Log on, tune in, find out. Another good idea from Cambridge.
It's a short announcement. If you came from the United States and if you were promised something from the NSF and NSA grants, you should find a form which you need to send to Oregon when you come back. Please do it as soon as you can. And if you have not been promised anything from that grant and you came from the United States, there's a chance you'll have money left, so please talk to me during this week if you on top of. Okay, so the next speaker is Daniel Nakano from Georgia. His title is on the book.
I'd like to first thank the organizers for the invitation to speak here. It's a real honor. So what I'd like to talk about today is atypicality, complexity, and module varieties. So these module varieties are both support varieties and there are both associated varieties. So there are several types of varieties I'm going to talk about in connection with these two numerical invariants. So I'd like to start by motivating my talk some. So let's start. Well, first, these are the references. So I'm going to talk about briefly work in the first two papers. These two papers tie in the concept of atypicality to support varieties and their dimensions. And then the third paper is the newest paper, which just was posted on the archive. And this will talk about the connections between support varieties and varieties introduced by Duflo and Serganova. And this paper here is an application of these concepts to the Lie superalgebra Wn. Okay, so let's start. Okay, so I'd like to first start by looking at the category O, the regular category O. So let me just review a few very basic concepts about the regular category O. So this is the highest weight category. What's this? Okay, and it has only finitely many simples. So if you pick a block, you have finitely many simple modules. And because it's the highest weight category with finitely many simples, the projective resolutions of the modules, they have finite length. So that means that there's not much cohomology there. The cohomology actually dies after a certain period of time. Okay, so the cohomology will only live in infinitely many degrees. And moreover, if you take the endomorphism algebra of a progenerator, like the direct sum of the projectives, then it gives rise to these finite dimensional quasi-hereditary algebras. Okay, now let's contrast that with the superalgebra situation. So let's consider the category F, which was introduced in John Brunden's talk. So these are finite dimensional modules for a classical Lie superalgebra. So for example, G being equal to GLMN. Okay, so these are modules which are completely reducible over the G0 portion. So their representation theory is slightly different. The categories are oftentimes highest weight categories, as observed by Brunden. However, they're now infinitely many simple modules. So again, this appeared in John's talk. Moreover, we have the property that F is self-injective. So if you take a projective module, then it's also injective. So that doesn't always happen in the ordinary category O. And also, projective resolutions could have infinite length. In fact, if you take a minimal projective resolution, it could just grow. Okay? So that means that the cohomology theory is potentially very interesting. So the cohomology can grow in dimension, so one's motivated to study these objects using techniques from modular representation theory. Okay. All right, so this slide sort of points to a previous talk. So what we're going to do is we're going to model our approach sort of on the study of finite group schemes. So this was mentioned in Friedlander's talk. So I just want to point out a few basic properties about finite group schemes. So they're the same as looking at finite dimensional co-commutative Hopf algebras. And we have a similar behavior to the previous slide. So A is a Frobenius algebra, meaning that you have projectivity if and only if you have injectivity. Okay? And also, you have this additional property that every finite dimensional module admits a minimal projective resolution whose terms have dimensions which increase at a polynomial rate of growth. Okay? So this is actually a fairly deep theorem. This theorem in order to prove this theorem, you need the finite generation of cohomology, which was proven by Friedlander and Suslin for finite group schemes. So once you establish that, you can actually prove that your minimal projective resolutions only have polynomial rate of growth. So we'll see if this actually happens for the category F. All right. So I just want to mention one basic point. So suppose you combine the two concepts. So suppose you have a Frobenius category and you have highest weight category. Well, if you only have finitely many simple modules, then A has to be semi-simple. So there's not much there if you have only finitely many simple modules. So the fact that you have infinitely many simples in your category is very important for you to have a non-trivial theory. So that's what we're going to sort of, that's going to be the major problem, but also the thing which makes things very interesting in the category F. Okay, so let me start with some basics. So we're going to fix G to be a finite dimensional Lie superalgebra. So this is a Z2 graded vector space. It has a G0 component and a G1 component. It has a bracket operation, just like with the ordinary Lie algebra, but it preserves the Z2 grading, and it satisfies graded versions of like the super Jacobi identity. So you take the Jacobi identity and you put -1 to the degrees there. Okay, so that gives you a definition of a Lie superalgebra. If you take GLMN, that's an example. Now, let me make the following definition. So we're going to say that a Lie superalgebra is classical if this part here, the G0 component, is the Lie algebra of a connected reductive algebraic group. Okay, we're assuming nothing about simplicity here. We're just assuming that we have a reductive group as our G0 component. And then what could happen is that the action of G0 on G1, it actually differentiates the adjoint representation. So a very natural condition that we just impose.
Well, the action of G1 on G1.
G1 on G1. So you actually get something in G0 again because of the Z2 grade. Yeah. So
it's not a part of this classical definition of being classical, right?
The action of
we're supposed to find some non-trivial commutators between G1 and G1, right?
Yes.
If you have an algebraic group, what can it be? If you have an interpretation through the algebraic group,
yes.
Right? You have G0, you have G1.
Yes.
You understand G0, G1, but still there is a mysterious thing how to define G1
yes.
with G1.
That's
right?
true. Yes.
Mm-hmm.
Yeah. There is. That's the non-trivial part about this game.
So you don't assume anything on simplicity?
No, we don't assume anything on simplicity. It's different from your definition. Good. Okay. All right, so this appeared in John's talk too, so let me briefly go over this. So this is an example of a Lie superalgebra. So you take GLMN, so you just take the set of n+1 by n+1 matrices. Your G0 component are just the blocks or matrices, block matrices, where A is an m by m matrix and B is an m by n matrix. Your G1 component, these are matrices where things are sort of off the diagonal here. And the super commutator relation is just given by this. So if you take EIJ being an elementary matrix and EKL being an elementary matrix, you can just compute out what the super commutator is using this formula. And then you can just extend linearly. Okay. All right, so F will be the full subcategory of GG0 modules. So GG0 modules are just modules for G which are completely reducible over G0. And with F, we're assuming the finite dimensionality condition. And here's a little bit more notation. So I'm going to let U of G be the universal enveloping algebra of script G. Okay? And this object will come up quite often in the talk. So if you take the G1 component, you take its dual, then you can look at the symmetric algebra on the dual of G1. Okay? So another way to think about this is going to be the super exterior product on this. And that's where cohomology will come into play.
So it's actually exterior algebra.
Yes. So it's yeah, in the super sense. That's right. Okay.
Symmetric algebra
No, it's the exterior algebra, the superset.
Is it finite dimensional or infinite dimensional?
Infinite dimensional. Yeah. Okay. Yes. Okay. So now we're going to say that G is basic classical if you have a non-degenerate, invariant, supersymmetric, even bilinear form. Okay. So for GLMN, this actually is true. And then once you have this form, you can define roots. Okay. So you have a set of roots for this, and then you can talk about even roots, and then you can talk about odd roots, and then you can talk about rho. So in the classical sense, rho is half the sum of the positive roots. But here, what you do is you take half the sum of the positive even roots and half the sum of the positive odd roots. You take their difference, and then you divide by 2.
If we first choose a positive set,
Right. Yes, you have to choose a positive set of roots.
which are not necessarily.
Right. Yeah. Okay. All right, so now what I'd like to do is I'd like to introduce some combinatorial notions that were defined by Katz and Wakimoto. So the first thing is a combinatorial notion on the Lie superalgebra. So this is called the defect. So with respect to the form, you look at the dimension of the maximal isotropic subspace in the R span of the roots. Okay, so this will give you a number, and this is called the defect. So here I have some examples. So if you take the defect of GLMN, this is the same as the defect of SLMN, and you just take the minimum of MNN. Okay, so that'll be the defect in that case. If you take these other Lie superalgebras, D21 alpha or G3, the defect is just going to be 1. Okay. So you can actually work this number out once you have the form. And then this is a definition, the atypicality. And so if you take a weight, you can define the atypicality, just like in John's talk. So you just take the maximum number of linearly independent, mutually orthogonal positive isotropic roots which satisfy this condition. Okay, so you sort of take an isotropic set, orthogonal, with this sort of common condition here, the stabilizer condition. Okay. And again, you can work that out for any weight. Okay, so one of our goals is we want to actually relate the concepts, these concepts, to some underlying geometry with Lie superalgebras. And so the way we're going to do that is we're going to use the cohomology theory in order to connect these concepts up with some geometry. So before I do that, let me present an example. So some of this was done in John's talk. So let's start out with GL11. So this is actually a very illustrative example of what's happening homologically. So the simple modules in the principal block, so we saw that they're one-dimensional. And they're also indexed by lambda minus lambda. So if you take lambda minus lambda, you get 0. Okay, so you're going to have non-trivial atypicality there. Okay, the projective covers will be labeled by lambda minus lambda with a phi. Okay. And as we saw yesterday, the projective covers are 4-dimensional, and they have the following structure. So if you take a lambda at the top, then the second layer is lambda minus 1, lambda plus 1, and lambda. So I should have bars everywhere, but you get the idea. So it's radical length 3. And then what you can do is, if you take the trivial module, you can easily construct a minimal projective resolution for the trivial module, right? So you have these maps which go into the projective covers by sending things into the second layers, okay? And then you just continue the process on, and you notice that this is 4-dimensional. Okay, the next one is 8-dimensional. The next term is going to be 12-dimensional, so forth and so on. So this minimal projective resolution has linear rate of growth. So in terms of its complexity, the rate of growth of the minimal projective resolution, the answer is 2. Okay. All right, now it can also be shown that whenever you take another irreducible module in the principal block, its complexity is 2 also. Okay. However, if you look at the cohomology ring, then the Kroll dimension of this cohomology ring is 1. And also the atypicality of the trivial module is 1 also. Okay, so, if you think about finite group schemes or group algebras, usually the cohomology ring here measures the complexity of the trivial module, but here it does not. Okay? And we'll see what the subtleties are later on. Okay, so now I have to talk about cohomology. So let's look at the relative cohomology for the pair G0. So this is obtained by a process which is like the ordinary Lie algebra cohomology. So you have to look at the exterior algebra, and then you have to, you have differentials which actually you construct, and then you sort of compute differentials. So here, instead of the ordinary exterior algebra, you have to take the super exterior algebra. Okay? And so these give you the cochains here. So given a module, you sort of build these cochains. Notice that you have to take Homs over G0 bar. Okay? So this was a theorem which was proved in our first paper. So the first thing is, if you want to look at x to the trivial module, or the x to the trivial module with itself in this category, then you can identify that with the cohomology. So this has a natural ring structure. Okay. And the nice thing is, if you compute the differentials, or you look at the formula for the differentials, then all the differentials are 0. Okay. So that's because whenever you take something in G minus, G1, and G1, if you bracket it, you get something in G0. Okay. So that's part of this, part of the formula for the differentials, which allow you to show that they're 0. Okay, so the differentials are 0, so the cohomology identifies with the cochains. That's this next line. And then when you take the super exterior algebra here, you just get the symmetric algebra. Okay. So what this says is that you have quite a bit of cohomology. So this cohomology is actually going to grow in dimension. And notice another facet of this is you have G0 bar. So you're taking the symmetric algebra with G0 bar invariance. So that already says that you're going to have to deal with invariant theory in order to solve problems. Now, remember, G0 is reductive, so that means that this is going to be finitely generated. So that's good news. So usually when you take a relative cohomology theory, you don't get finitely generated cohomology. But in this case, everything's nice because this is a finitely generated ring. Okay. All right. So now what we do is we look at the action of G0 on G1. And you can think of this theorem here as a generalization of the Chevalier restriction theorem. So this is, you think of as a symmetric algebra on G1 with G0 invariance. And this is the symmetric algebra of E1 with W invariance. And W is a finite reflection group. So this theorem allows you to actually detect all the cohomology on a smaller subalgebra. So this is very reminiscent of the picture you have for finite groups, for example, where you have like the CELO subgroup over here, where you can sort of detect everything on the CELO subgroup or on elementary abelians. Okay. And this E that we actually construct in this theorem is isomorphic to a direct sum of these, the Lie algebras Q1. Okay, so they're not quite, you're not quite using nilpotent operators here, because if you take something in the E1 component, you get something in E0. So the representation theory is slightly more complicated, but you can still deal with it. It's not so bad. So what it says is that if you want to look at the cohomology, you can actually compute it by looking at this ring of invariance over here with the finite reflection group. So immediately, this is going to be just a polynomial ring. Okay. And when you do this, something automatically just pops out. So if you take a basic classical simple...
Why did you put simple?
Because we might do this for GLMN, for example. This is
almost.
Yes, almost simple, yes. So that's why it's in parentheses. So something automatically pops out by this construction. So if you assume that G is not PSLN NN, then the defect is just going to be the dimension of the cohomology ring. So this invariant that was defined by Katsuwaki-Moto appears as just the dimension of this ring. Either you take GG0 over C or EE0 over C. And that's just the dimension of the subspace. So this gives you a nice interpretation of this defect, which is kind of surprising. Well, one thing that's interesting is this notion of defect. I think I asked Victor this about 2 years ago. So there's defect for finite groups, and there's defect here. But I guess there's no coincidence, even though a lot of these properties coincide. Okay, so let's continue on. So now we have to talk about how we can do things with the atypicality.
Do we have some maximality principle that this E is maximal among all which are direct sums of Q1s?
There might be an invariant theory.
Maximality.
Yeah, I think there might be a property, it's an invariant theoretic property, which, yeah. Because there's some conjugacy statements too, so that you can.
But with this Q1, that just is 2 by 2 matrix.
Yes. Right. Yeah, that's right. Okay, so we actually established the finite generation of cohomology for modules too. So if you take x div mm right here, then it's going to be finitely generated over this cohomology ring. We had to use results of Popov and Winberg to do this. So, so right now what I'm just presenting is a definition of the support variety. So this is a cohomological definition of the support variety. This is different from what Eric presented this morning. So what you do, this is a standard thing that one does, is that you look at h of GG0 of m with its dual. Now, this ring is going to act on this on this module over here. And then you just look at the annihilator of the action of this ring on this module. And you quotient out by the ring, or quotient out by the ideal, sorry. And then you just take the maximum ideal spectrum. And that'll give you the support variety. So you can do this for G, and you can do this for E too. Okay. So this support lives inside of G1 factored by G0 bar. This support lives inside of E1. Okay, so one thing you can immediately prove is an inclusion of these support varieties. So if you take VEE0 of M, so suppose you start with a G module, and if you factor out by the action of W, that's going to inject into this support. And it turns out that it's an open question and an open conjecture that this map is surjective. So we think it's going to be surjective. We know it's surjective in many, many cases, but we still have not been able to prove this. And part of the reason we can't prove this is that we have a rank variety description, or a pi point type of description here, but we don't have a description in terms of like pi points over here. Okay? If we did, then it probably would either be true or not true, but we don't have that concreteness yet. Okay. All right, so here's the conjecture. So suppose you take a basic classical Lie superalgebra. So we know, so you can take a weight, okay, and you could compute its atypicality. So we think it's going to be the dimension of this support. So the support over E0. So you can define, so this is for our highest weight module V lambda. Finite dimensional, right. Finite dimensional, highest weight module L lambda. You can look at its atypicality, and we want to know whether it's equal to the dimension of the support variety. Now, one way you can think about this conjecture is that if it were true, then the natural notion of atypicality should be given in terms of support varieties. So if this was true, then you can extend the definition of atypicality to all modules in F. So right now it's just dependent on weights. So it would be nice to have a functorial definition of atypicality. And that's what this conjecture will allow you to do. Okay, let me say what the good news is. So the good news is that it's actually true for GLMN. Okay, so what I'll do is I'll describe what the support varieties for the irreducible modules are in this setting. All right, so suppose that you take GLMN. R is just the defect of G, so that's just the minimum of M and N. And suppose you take a finite dimensional simple G module, and let's say it has atypicality K. Okay. So we want to know first what the G0 support is. So it turns out to be just isomorphic to an affine space. Okay. And it turns out that this map that I had mentioned before, restriction star, is actually surjective in that case. And it takes this support variety here onto the affine space over here. Okay. Now, what we can also do is we can also describe what the E0 support is. So you can construct this E1 tilde, which also has dimension K, K being the atypicality, and then you just take this W that I constructed before, and then you just smear this plane around. It's a finite reflection group, and so this VE0 support will just be a bunch of planes, okay, just kind of put together using the W action. And notice that if you factor out by the action of W here, then you get this, just this affine space. So it's very consistent with what I mentioned before. Okay, so for GLMN, you can actually define the atypicality for any module you'd like using this definition of the support. Okay, any questions up until this point? Sort of a break in the talk. Okay. All right, so the next thing I'd like to talk about is this notion of complexity. So I presented this example before for GL11. So the complexity of the trivial module, I had complexity 2, although the atypicality was 1 for the trivial module. So we can formally define the complexity just like you would do for group algebras. So first of all, you have to define the rate of growth. Okay. So if you have a sequence of vector spaces, then you can define the rate of growth as taking the smallest constant c, such that the dimension of this vector space is sort of bounded by just a polynomial of dimension or degree c minus 1. So dimension vt is less than c times t to the c minus 1. All right, so if no such integer exists, then v has infinite rate of growth. It can happen sometimes. And so if you take a minimal projective resolution for M, and this is following Alprand, who defined this in 1977, we define the complexity to be just the rate of growth of the minimal projective resolution for M. Okay. So this was, historically, this was sort of the start of support variety theory. He defined complexity, and then they actually showed that when you define these supports, then the support variety actually equals the complexity of the module. Remember, it's not true in this case. Only for group algebras and restricted Lie algebras and so forth and so on. Okay. Now, the question that we had at MSRI, so this is a question which came up during John Kujawa's talk, was if you take a Lie superalgebra, let's say a classical one, is the complexity going to be finite for any module? Okay, so for GL11, we know it's going to be finite. But what about in general? So this actually answers the question. And we have an effective upper bound for what the complexity is for any module. So if you take a module in F, then one thing we can immediately say is that the complexity is an invariant of projectivity. So the complexity is 0 if and only if M is projective. So this sort of follows immediately from the self-injectivity of F. Okay, that's standard argument. Now, for part 2, how do we show that the complexity is bounded by the dimension of G1? Well, what we do is, this is just a sketch of what we do. So we take the trivial module here first, and then we just find a projective resolution for the trivial module. So this projective resolution is quite natural. So it involves looking at the exterior algebra, super exterior algebra of G over G0 bar, tensored up from, so there's an action of U of G0 on this, tensored up to U of G. Okay, so that's what the DPs are. And let's look at each of these terms. So this is going to be really the symmetric algebra, because these are odd degree elements. So this will be the symmetric algebra on G1 bar here. And if you take a cobasis over here, what are you going to get? You're going to get the finite exterior algebra on G1 bar, right? Just by using the PBW theorem. Yeah. So this finite part's not going to matter at all. What's going to matter is the rate of growth here, and so that proves that the rate of growth of this projective resolution is the same as the Kroll dimension of this cohomology ring. Okay? And now if you take any module, you can tensor it by this resolution, you'll get another projective resolution, and so that resolution will have rate of growth, Kroll dimension of the symmetric algebra, and that proves this statement up at the top. Okay. So one thing we don't know is, given the trivial module for GLMN, what's the complexity of the trivial module in general? We know it for GL11, but we don't know it in general. Okay? So that's an open question. Okay. So what we can say is that you can relate the complexity to some rate of growth involving the cohomology. So if you take a minimal projective resolution, and if you take this direct sum, so this is actually well, this has infinitely many terms in it because you have infinitely many simple modules. So if you take this direct sum, and you go out of the category after, so you have to look at GG0 cohomology, then if you take the x of this, then it turns out if you take its rate of growth, that's equal to the complexity. So normally you can just take a finite set of simple modules, and this would be true. And that's why, in some sense, whenever you take the Kroll dimension of the cohomology ring, then it's equal to the complexity. But here's what's showing you the difference, that here you have to take an infinite sum of simples, and so it's never going to be the case that when you do have an infinite sum of simple modules, it's going to be the Kroll dimension of the cohomology ring. Okay, there's extra stuff going on here. Okay, so I'll come back to this topic at the end of my talk. All right, so now what I'd like to do is I'd like to talk about type 1 Lie superalgebra. So what we'll do is we'll look at other module varieties, and it turns out that these module varieties will allow us to detect projectivity for type 1 Lie superalgebra. So the content of this part of the talk is in the third paper on the archive. All right, so let's start out with the type 1 classical Lie superalgebra. So in addition to being Z2 graded, it's also Z graded. And the Z grading is compatible with the Z2 grading. So the G1 bar component will consist of the direct sum of G1 and G minus 1. The G0 component will consist of G0. Okay? So GLMN is a classic example of a type 1 Lie superalgebra. The G0 component is just the GLM cross the GLN. The G1 component was like the sort of the upper triangular matrices off the blocks, and then the G minus 1 component is the sort of lower triangular ones. Okay. Now, what you can do is you can sort of think about this like a Levy decomposition, and you can form these P pluses and P minuses. So these are like parabolic subalgebras. So G1 is an ideal inside of P plus, G minus 1 is an ideal inside of P minus. And then for the G0 part, let's fix maximal torus. So H will be a maximal torus in here, and then you choose a Borel subalgebra containing that maximal torus. Okay, so first of all, the next thing I'm going to do is I'm going to define the Katz modules. Okay, so you take the set of dominant weights, X plus. So these are highest weights for the simple finite dimensional G0 module. Remember, G0 is classical with respect to the pair HB0. So let's label that by L0. So this has highest weight lambda. And then just inflate this module to P plus. Okay? And then you just build these modules. These are like generalized Verma modules. where this is just inflation of P plus, and then you induce up to V of G, U of G. So this is the Katz module highest weight lambda, and then the dual Katz module we'll define by using the HOM. Okay, so the U of G is a bimodule for U of P minus and U of G, so this is going to be a left U of G module. Okay, so these are very, very standard constructions. Now, these are going to play the role of the intermediate modules in the category. So projectives are going to have filtrations by these Katz modules, and it turns out because of self-injectivity of the dual Katz modules too. So this category F for these type 1 least superalgebras is the highest weight category, as I mentioned at the beginning of my talk. And this category is also self-injective too. So again, we have both sort of factors playing a role in the theory. Okay. All right, so I define support varieties for the pair GG0 and also the pair EE0. So this is my second set of varieties that I want to define. So these are going to be supports for G1 plus and G1 minus. Okay, so if I take G1, this is an abelian least superalgebra. But here, again, we have to be careful. We have to take the exterior algebra, super exterior algebra, when we compute the cohomology, which turns out to be the symmetric algebra. So this turns out to be good. So again, the symmetric algebra is coming up again in the game. And so let's say you take G1 supermodules. Then you can define this support variety just as you normally would. You just take the annihilator of this ring on the cohomology. So this should be a C, not an F. Okay, and it turns out that in this situation, you can make an explicit, concrete realization of the supports. Okay, so you have a cohomological definition, but then you get this rather natural and familiar concrete definition of the support. You just take all x's in G1, where M is, I guess, not projective as a U of X model. So there should be a not here. Okay? And so that means that these supports are canonically isomorphic to a rank variety. So they have sort of a pi point description. And the nice thing about these supports is they do detect projectivity. So if you want to know whether it's projective over G1, it's going to happen if and only if this support's going to be 0. Okay. So the next thing I'd like to do is I'd like to show you that these support varieties can be used to detect Katz filtrations and dual Katz filtrations. All right. So let's say I want to know whether a module has a Katz filtration. Then there's a sort of the standard criterion for having a Katz filtration given by this X1 criterion. So you take the dual Katz module, you see whether the X is 0. For all dual Katz modules, then you know that M has a Katz filtration. But with these support varieties, we can actually, say when something has a Katz filtration by just determining whether this support is equal to 0 or not. So if M has a Katz filtration, this happens if and only if the support variety over G minus 1 is equal to 0. Okay. This is the projectivity condition too, over G1. Okay. So you can also do this. This is the advantage with slides, so I don't have to write this twice. Okay. So now you can also do this for dual Katz modules also. And so M has a dual Katz filtration if and only if the support variety here is equal to 0. This is for G1. Okay? So this gives you necessary and sufficient conditions to have a Katz filtration and a dual Katz filtration. Okay, so now we just make the definition. A module is tilting if it has both a Katz and a dual Katz filtration. So let's just combine both theorems. So now what can we say? We can say that M is tilting if and only if VG1 of M is 0 and Vg minus 1 of m is equal to 0. Okay? So this gives a necessary and sufficient condition for when a module is actually a tilting module in this category. Okay, so now where's the connection with projectivity? Okay, so here's a theorem that, so this is a theorem that we don't want to cheat. Okay, so Duflo and Serganova actually have a criterion for projectivity. Well, we're not using it in this theorem. That'll come up later on. So we can actually prove independently of Duflo and Serganova that if you take a module is projective if and only if you have the same thing happening. Okay, so the same criterion that I presented over here happens, then we know the module is projective too. So an interesting, the proof uses some old work of Klein, Partial, and Scott on injective modules for GRT. So there's a paper on GRT for injective modules, and they have a statement that says a module is projective for GRT if it's projective over BRT and BR plus T. So we just take that proof and we just apply it in this situation, okay? And we get this out. So combining this statement and this statement up here, then a module is projective if and only if it's tilting for F. Okay? So this theorem was originally proved for GLMN and some other contexts by John Brundon. So this is a generalization of a theorem that was proved by John Brundon. And I believe John used combinatorics to prove this. Is that right? Sort of, yeah. Okay. So this is a support variety proof for this work. Okay. So now I'll show you how these supports that I constructed are related to the varieties of Duflo and Serganova. So I have to review what their varieties are. So they define the following varieties. So you take an x in G1 such that the square, so you take the bracket of x with itself, and you have to divide by 2, that's equal to 0. Okay, it doesn't matter, we're in characteristic 0. So. Okay. Now, if you take an m and f, then they define the following variety. So this was the original definition. So you consider x in this script x up here as an operator from m to m, sort of a nilpotent operator. And you look at the kernel mod the image. And you want to know when it's non-zero. So again, this is the same as when x is, I keep on forgetting the not, is not projective as a u of x module. Okay. So this looks like a support variety condition or rank variety type of condition. Okay. All right, so now you just, so this is rather trivial just by the definitions. So remember, this thing has a rank variety description, okay? This one has a ranked variety description. So if you take the union of the two, it has to sit inside of x of m. Okay, you're just using the definition of x of m and the realization of these two in terms of rank varieties. And then you can also say that if you take x of m and if you intersect it by like G1, then you get the support variety for m. Okay, so we don't know if there's any cohomological description for x of m. I mean, that's still open. We don't know whether this x of m comes from any cohomology theory. But we do know that these two varieties are connected or do have some cohomological interpretation. Okay, and that turns out to be good enough for certain applications. So this theorem was one of the main theorems that was proved by Duflo and Serganova, and it was proved in a wider context than just these classical type 1 Lie superalgebras. But for this,
They did it for all.
yes, they did it for all. But here we can actually just oh, okay. So here we can actually just prove their result by using what I've mentioned. So we can say that a module is projective if and only if this x of m is 0. Okay, so one direction is quite clear, because if x of m is 0, well, that means that this is 0 and that's 0, and that means it's tilting or projective, so that immediately follows. Now, suppose you have m being projective, and suppose x of m is not 0, so then you could write an element, let's see, let me just erase this for a second. So suppose m is projective. So this means that v of g1 of m is 0, and v of g minus 1 of m is equal to 0. But it turns out that if you take an x in script x of m, then you can write it in terms of g minus 1 and g1. So something in g minus 1 plus something in g1. But then, because your module is actually a module over an algebraic torus, okay, which actually picks up the grading between these two, you can use an old trick that appears in a paper by Friedlander and Partial to drop one of these elements inside of the intersection. So this means that x minus 1 is in x of m intersection g minus 1, or x1 is in x of m intersection g1. So actually it's and. Okay, and then because these are 0, these two have to be 0, so that proves that x is 0. Okay,
You
so
want the model to have a rational model structure for the torus.
right, but that happens because m is a module for the Lie superalgebra already. Okay, so things are fairly rigid in that sense. So you already have these compatible gradings that are happening. Okay, so now the question is, can we do better? And the answer is yes. So, at first this slide might seem really intimidating, but let me show you in the context of GLMN what this slide means. All right, so first of all, if you take a type 1 Lie, a classical Lie superalgebra, oops. Oh well, see if this one works. Okay, and so suppose that you look at the action of G0 on G1. Okay, so actually you're going to look at the action of G0 on G minus 1 and G1. And you can look at a set of orbits on these, on G minus 1 and G1. And so all you have to do is test projectivity over the minimal orbits. Okay? So let me show you what happens in terms of GLMN. So let's say I take G being equal to GLMN. Okay? So what is G0 bar? That's GLM cross GLN. Okay? And let's just look at G1, for example. Okay, so G1, that's going to look like matrices of the form where entries lie up here. So what is the action of G0 on G1 going to look like? So let's say I take a pair, AB. So this is in GLM, this is in GLN. And if I take a matrix X, so an X in here, then if you conjugate, you'll just get AX B inverse. Okay? So what are the orbits? So this is this GLM cross GLN acting on M and K, so M by N matrices. So all you're doing is you're just picking out things in terms of ranks. Okay, so for GLMN, you just have to pick a rank 1 matrix in G1, test projectivity over that, take a rank 1 matrix in G minus 1, test over that, and if it's projective over those two elements, then it's projective over the whole algebra. So for this one, you just need to test projectivity. So here, test projectivity over just a rank 1 matrices. Just a rank 1 matrix. Okay. So I don't know, maybe someone knows the answer to this, but it appears that, I mean, these are determinantal varieties, and maybe there's some connection with determinantal varieties in these superalgebras happening here. So this happens in the other cases too. You sort of look at ranks in some sense, and it'd be nice if one could make some, obtain results about determinantal varieties using, the theory of least superalgebras. It's just an aside. Okay, so in my remaining time, let me just mention a few problems which we find rather interesting. Okay, so here's the first problem.
Excuse me, it looks
Yeah.
like a grammatical simplification. If you can reduce it to rank 1, right?
Yes.
Could you comment? Probably there are some hidden difficulties. You need to examine all orbits, right, or something like this.
No, you agree that's true.
Actually, it follows from our work.
Right, it does, yeah.
Because you look at the orbits, and
Right.
the biggest orbit is
I understand, yeah.
why we look at it.
Right. Okay, so now if you look at finite dimensional co-commutative Hopf algebras, so there's actually a formula. Whenever you take a projective module for a finite dimensional co-commutative Hopf algebra, then you know what the socle is going to be. Right? There's a nice formula in Janssen's book. And so a general question we'd like to know the answer to is, that's not type 1. Suppose you have a projective cover for a simple module in F. Then we know it's injective. So it's the injective whole of some t. So what's the relationship between S and t? Okay, so for type 1 least superalgebras, we can cheat because everything is tilting. So that's okay. But for general classical least superalgebras, we don't know the answer. So there should be a nice relationship between S and t and
What is S?
oh, okay, so S is a simple module in F.
Ah,
Okay, so P of S is its projective cover, but we know that the projectives are injective also. So this should be the injective whole for some t, right? So we want to know the relationship between S and t. Okay, for arbitrary.
always P like coincide.
They what?
Coincide.
They coincide for like the type 1 situation.
Type 2 rules.
Oh, really? Okay, so I
I'll
don't.
tell you later.
Okay, so maybe, but what about in general for like, arbitrary?
I think we can discuss later. I think I know the answer.
I don't think they coincide all the time. If you take like.
I don't say they always coincide.
Okay, so maybe there's an answer. All right. Okay, so here's another interesting question. I think John answered this question in his talk for GLMN. So if you take a simple module in F, can one give a concrete realization of this endomorphism algebra? Okay, so if you knew this, it might contribute to a solution of 1. Okay, definitely related. And then here's kind of the big question. So we know that the complexity is finite. So what we'd like to know is there some variety theoretic description such that if you take this variety for a module M, its dimension will equal the complexity. Okay, so that's open still. So is there some other geometric object that you can construct which will actually measure the complexity? Okay, so that ends my talk.
How do you parameterize the irreducibles in thinking about number 3? Because that's what's...
Oh, parameterize. So if you take type 1, then you just sort of parameterize them by highest weights.
You're not... You could somehow put some geometry into the parameterization of the irreducibles. You could build that into your...
Right.
Yeah.
That might be a possibility, yes. I agree. Yeah. So this is another reason we were studying that. We're actually looking at Ballmer's theory, too, which might be quite relevant for this situation. Yes.
Which homologically support varieties can appear generally in this picture? Do you have some extra structures like whatever, symplectic structures or whatever structures?
We actually don't know. I mean, in fact, well, okay, so let me say what we do know. So if you take, so we actually proved a realization theorem for G. So if it turns out if you take a subvariety, so if you take W conical inside of VGG0 of K of C, so there exists a G module, let's say called M, such that its V of GG0 support is equal to this W. Maybe use a script here. Okay, so you can actually realize everything. This appears in that fourth paper with Boxy.
You're either assuming W is closed or M is
Yeah, so this is conical closed subvariety. Closed, yes, subvariety.
Invariance on the group.
No, because you don't have an action.